Okay, just doing a test. All right. So welcome to Lab 4 of Geography 270. So we're basically halfway through the lab series for this course. So in today's lab, we're going to be looking at using a couple different programs that we already use, Excel, but we're going to mostly be using JASP again. And what we're going to be doing in this lab is we're going to be computing the 95% confidence interval, as well as the 99% confidence interval. And then we're going to be looking at performing 3 types of t-tests. So t-tests are what we're going to be looking at in this week's lecture. So we're going to be doing each of these 3 types of t-tests in this lab. And there's more information for each of these types of t-tests in the videos embedded in the lab itself. One statistic that we haven't looked at in the lab or the lecture yet is something called effect size. And the effect size is often described in this lab anyways by the Cohen's d. So what Cohen's d basically tells us, as the Cohen's d value gets larger, that tells us that there's a greater difference between 2 data sets or samples. So as that Cohen's d gets larger, again, that indicates that we have a greater difference between 2 groups of values. So you're not going to be calculating it by hand. You're going to be using JASP to calculate Cohen's d. So the first file we're going to be looking at, so in the Moodle folder there, is Mason Lake 95 _ day of your year number 4. Right, so here's the variables, right? So it's split between 2 sites, the J1 and the J4 site. We're going to be mainly looking at snow depth data. So question 1 deals with calculating confidence intervals. So the first thing it asks you, once you got your data file in JASP, is to calculate the descriptive stats of mean, standard deviation, and standard error for depth for both the J1 and J4 sites. And then you're going to be going down and entering the upper and lower bounds of both the 95% confidence interval for each site and the 99% confidence interval. Remember from the lecture that the confidence interval, right, gives us a range. It gives us an idea of the probability that that range is going to capture something like the population mean. So you might be wondering, why are these z-scores 1.96 and 2.58? Well, those z-scores correspond to a 95% confidence interval, right? A z-score of 1.96. And then if you go out even further, that corresponds to a lower end of minus 2.56 or 2.58 and a higher end of 2.58. So you can calculate the standard error of the mean automatically in JASP underneath the stats pull down menu right there. You can also enter the confidence or do the confidence interval for the mean by clicking that button. So just to go over a calculation of a confidence interval, say we have a sample of 100 pebbles from a beach in Vancouver Island, and that 100 sample of rocks has a mean of 8.5 centimeters for a diameter, with a standard deviation of the diameter of 1.5 centimeters. How would we calculate a confidence interval for this data? Well, first of all, we have to calculate the standard error, which we know is given by the sample standard deviation divided by the square root of the sample size. And for this example, that would give us a standard error of 0.15. Now we can use that standard error to construct our confidence intervals. Now, a 68% confidence interval corresponds roughly to plus and minus 1 standard error above and below the mean, right? But we don't want a 68% confidence interval. We want something higher. We want a 95% confidence interval to begin with. So how can we calculate that? Well, we take the z-score, which corresponds to the 95% confidence interval, and multiply it by the standard error. So for the case of the 95% confidence interval, it has a corresponding z-score of 1.96. We multiply the standard error by that value, and it gives us the 95% confidence interval, which is 0.294 centimeters above and below the mean of 8.5 centimeters. So we have a lower value for the 95% confidence interval of 8.21 centimeters and a higher value of 8.79. So this tells us we can be 95% sure that the overall population mean is going to fall within that range, or AKA that interval. But say we want to be even more sure that our interval is capturing the population mean. So for this case, we're going to calculate the 99% confidence interval. So now we are dealing with a different z-score, but we're going to do the same operation. Our z-score for the 99% confidence interval is 2.58. We multiply our standard error by 2.58, and that gives us a much larger confidence interval. So now we can be 99% confident that that interval is going to capture our overall population mean. Second part of the lab has to do with t-tests. And again, we're going to be dealing with 3 types of t-tests in this lab and the lecture. First one's called a one sample t-test, where we're using the test to determine whether a sample mean belongs to an overall population. Second one is called an independent samples t-test, where we have 2 samples, and we're using a test to determine whether those samples come from a common overall population, or it's more likely that they come from different populations. And then the third type of t-test is called a pair samples t-test, where we're seeing if there's some difference in a variable. In the case of our lab, it will be snow depth over time. Right, so since I have not gone over the t-test yet in the lecture, and they will be in this week's lecture, I'm going to delay the submission due date for this lab 1 more week, so it won't be due till March 18th. This will allow you to have some time to go over the lecture videos and slides that discuss t-tests. So I've just submitted or put these on Moodle. So these are the lecture slides and videos. If you want to check that out to have a better idea what t-tests involve before you do the lab, you should have lots of time to do that. All right, so let's look at our first question 2, that has to do with t-test. So the idea, the scenario of the question is that you have a sample of mean annual air temperatures recorded at Kelowna Airport from 1993 up to 2004. So this is our sample data set right here. We're wondering if this sample data set comes from an overall larger population data set, which spans over a larger time period going from 1981 to 2010. So essentially, we're seeing if this sample belongs to the larger overall population using the one sample means t-test. So for this type of test, our null hypothesis is that the sample comes from the population. So that's our default assumption. And if our test tells us to reject that null hypothesis, we're going to conclude that the sample comes from a different population. So this is essentially what you're going to be filling in when you run the one sample t-test, right? So you're going to be running it in JASP, and you're going to be entering the t-stat there. There's our degrees of freedom. There's the p-value, and then there's the co-inst. And then based on those values, you're going to be answering whether the mean of the samples is statistically significantly different than the population. Is there a strong effect size given by the co-inst value? And based on that, do you reject the null hypothesis? And to do this test, use a confidence interval of 95%, otherwise a alpha value of 0.05. Okay, so for this question here, you'll have to create your own CSV file to load into JASP, so you can copy the data directly from the lab, and you can paste it into an Excel spreadsheet. So once you have it pasted in Excel, go to File, go down to Save As. Remember, you do not want to save it as a regular Excel file. You want to save it as a CSV file, common separated value. So I'm going to put it somewhere on my desktop. So I'm going to give it a name here, Geography 270. Let's see, I'm just going to call it airport temperature. All right, and then save as type. I want to make sure I go up to CSV, common delimited, and actually already have one there, so I'm just going to overwrite that CSV file. So once I have the file loaded, I can go and open it up in JASP. I'll browse my computer. There's the CSV file right there. And there's my data. There's my sample data. So to do the t-test, I want to do the one sample t-test. So I select it under classic. I only have one variable, so I'm going to put that in the variable window. And I'm doing a student. And I want to enter the population mean as the test value. And then there's for my Cohen's d, my effect size. And that's basically all you need to do to answer the first one sample means test. The next question, you're going to be doing an independent samples t-test. So for this question, you're going to be entering another data file, CSV file, Mason Lake 95, day of year 4, right? That was the one you, I think, already entered into JASP. So you're going to be seeing if there's any significant differences in snow depth on day 4. Remember that the first thing you're going to do is going to be using your descriptive stats to calculate the mean, standard deviation, standard error for each of these data types. Right. So again, you're going to be looking at the variable of snow depth. So for this independent samples t-test, the null hypothesis is that the samples come from the same population. And if you reject that, the samples you're going to conclude come from different populations. So before we can do the independent samples t-test, we have to do something called a Levene's test, which tells us whether there is sufficient equality of variance between our two samples. So for the Levene's test, the null hypothesis, the default is that the variances are equal. Only if the Levene's test tells us to reject, we're going to conclude that the variances are not equal. So this is kind of like a hurdle you have to go through before you do the test itself. So to do this, I'm going to go to my independent samples t-test. I'm going to go put my depth variable, and I'm divided by site. I'm going to keep my test on student. Here's my alternative hypothesis. And then down there, I'm going to click on equality of variances and Levene's. So that will give me the data I need to know in order to tell whether my two data sets have sufficiently equal variances or not. Right, so once you have that data, and you're going to run the independent samples t-test, right? There's our t-stat for this test, the p-value, again, the Cohen's d effect size, and then based on that and how you interpret it, again, use a alpha value of 0.05 to compare the p-value to. You're going to determine whether the snow depth at the two sites is significantly different or not, and based on that, do you reject the null hypothesis? Okay, so for the last question and the last t-test, we're going to be doing the paired samples t-test. We're going to be using a different file that's found in Moodle, the Mason Lake 95 CSV file. All right, so the first thing you're going to do again is calculate, and what this file shows us is snow depth, not based on two different sites, but on two different days. So this day, DOY, stands for day of year 4, so like January 4th, and DOY 93 stands for the 93rd day of the year, so probably sometime in April, right? So you're going to be, for both of those times, you're going to be determining the mean, standard deviation, and standard error again. Right, so this is what the data looks like. So essentially you can think of the day of year 4 being the before variable, and the day of year 93 to be the after variable. So you're seeing if there's a significant difference in snow depth between day of year 4 to day of year 93. right? So the way that you enter it, you go into the t-test tab again. This time you're going to be selecting paired samples t-test, right? You plunk both of the variable pairs into the window here. The question also asks you to get the what's called the Wilcoxon sign rank output, which is the non-parametric version of the student's t-test. So select that button there, and that'll populate in your table. You're also going to be asked in this question to test whether the data is normally distributed. So we're going to be doing the Shapiro-Wilk test like you've done in the previous lab, right? Again, use a alpha level of 0.05, compare that to the p-value. If your p-value is less than the alpha value, you're going to reject the assumption, the null assumption, or the null hypothesis that your data is normally distributed. And then finally, based on running the paired samples t-test, right, you're going to be entering your t-value, your p, your Cohen's d, using both the student t-test, so that's the parametric version, and the non-parametric Wilcoxon test. Again, using an alpha value of 0.05 to determine whether you're going to reject or not. You're going to be answering the last questions. Is snow depth significantly different on day 4 relative to day 93? And based on that, are you going to decide to reject the null hypothesis or not? So again, with this paired sample t-test, the null hypothesis is that there's no significant differences between the before and after snow depth. If you reject that, you're going to assume that there is a significant differences between the before and after snow depth. Okay, so I'll let you guys work at it. Again, you have 2 weeks to complete this lab. So again, get a hold of me if you have any questions.